All right. So, well, real quick, just for the video's sake, here are some of your other functions that you need to know the integrals of. So, of course, make sure that you get those down. We are continuing with more indefinite integrals and some of the different rules in which you can take the antiderivative of different types of functions. So, here's one. We're trying to find the integral of x times the square root of x plus 2. Okay? For this one, which rule or what method can we go about finding the antiderivative of for this one? We're going to use substitution. If I use substitution, that means I'm going to make u what?
X plus 2.
Which means that du is going to equal what? 1 dx. Now, there's just one problem to this. I have an x left over. And so we're not going to want to multiply by x because then that's adding in another variable. Okay? Not divide by x. Not divide by d, huh? I didn't hear what you said. No, we wouldn't be able to do that. We want to make sure it's all in terms of u. What we can do though, remember, like in some of the problems that we were going over earlier, you can multiply things to both sides, or you can adjust. As long as you do it to both sides, it still holds true. What we can actually do is take this top part. If I were to subtract 2 to the other side, that would equal x, would it not? So now I'm allowed to rewrite this and say that I'm going to replace x with u minus 2. I'm going to replace x plus 2 with u. And now I have my du, which replaces dx.
Smart.
So now I'm able to find the antiderivative of this function. I am going to rewrite the square root of u as u to the 1/2. Then probably do what before I actually take the antiderivative? Then probably do what before I take the antiderivative? Distribute. So that's going to be u to the
3.
And then minus 2u to the 1/2. All right. Finish off this problem. Finish off this problem. All right. So we're taking the antiderivative of u to the 3/2 minus 2u to the 1/2. What is it?
2/5.
2/5.
X plus 2.
All right. So we're summing it back in. So 2/5. No, it's fine. X plus 2 to the 5/2.
Minus 3 or 2/3. 2. Yes. What is he? 2/3 or 4?
What's the exponent?
2 3 2.
It'll be 3/2. So then it's going to be, because of this coefficient out here in front, it's actually going to be what? 4/3. It's going to be 4/3. And then, of course, we cannot forget our, let's see. Okay, so do realize that that's also something else that can be added in with u substitution. Okay, making that adjustment just in case if you know you do everything right and you're like, wait, I still have something left over. You might have to adjust that original u so then that way you can substitute it back in terms of u. Okay. All right, let's keep on going. Remember, today it's all about some more indefinite integrals. Okay. Let's talk about partial fractions. We talked about this a little bit when we were dealing with rational functions. Okay. When we were talking about rational functions, we were able to decompose, break down a rational function as the sum of partial fractions. We want that same skill to integrate these types of functions. Okay. So these are called partial fractions. Okay, here's some examples with partial fractions. Here's an example. We're going to take the antiderivative of 7x minus 1 over 2x squared minus x minus 1. Hey, real quick, online, am I still good? Am I glitchy? Can you still hear me?
Yes.
It lagged for a second earlier, and then now it's fine.
Okay, because I just got a notification that said my connection was unstable. So, but like now I'm good.
Yes.
Okay, cool. All right. So let's take the antiderivative of this one. First off, u substitution is not going to work here. Okay, because even if you try to make the denominator your u, there's no way that you're going to be able to adjust and alter to get a 7x minus 1 for your du or anything like that. Okay, so this is where you want to create your partial fractions. First thing you want to do is you want to factor your denominator. How does 2x squared minus x minus 1 factor down? Factor 2x squared minus x minus 1.
X minus 2, x plus 1.
Then you have to divide bottoms up.
Oh, sorry, and then x minus 1, 2x plus 1. Yeah.
Very good. X minus 1 and then 2x plus 1. Very good. So essentially, what 7x minus 1 over 2x squared minus x minus 1 can be written as some number over x minus 1 plus another number over 2x plus 1. Your goal is to figure out what those two numbers are. We did this towards the beginning of last year, first semester, when we were going over rational functions. So I know y'all probably rusty. So this part right here is a review of rational functions, and then we'll apply the integration stuff with it, okay? So again, we're creating partial fractions here. So essentially what is happening is that we need to figure out the value of a and b. So that means we got to look at our numerator. It's going to have to equal 7x minus 1, the sum of these numerators. Well, think back to rational functions. In order for me to be able to add these, they have to have a common denominator, correct? Mm-hmm. Which means this first fraction with the a has to be multiplied by 2x plus 1. The one with b has to be multiplied by. So if you go ahead and do that and solely concentrate on the numerators, then what we're able to do is we're able to create a system of equations that's going to allow us to find the values of a and the values of b. Because 7x has to equal whatever a times 2x is plus b times x is, and negative 1 has to equal whatever a times 1 is and b times negative 1 is. So it allows us to create this system where 7 is equal to 2a plus b and negative 1 is equal to a minus b. So everyone see what I did there? Mm-hmm. Try to color code underline it.
Fancy.
So solving this system, you see our b's cancel out. What's 7 minus 1?
6.
And 2a plus a?
3.
So a is going to equal 2. And so then I can use that and plug it back in to find out that b is going to be equal to what number?
Minus 2, 3.
So I'm equal to 3. So using this information, I'm able to see that this function, this integral, can be written as the integral of a, which is 2, over x minus 1 plus b, which is 3, over 2x plus 1, and I can take the antiderivative now of that rational function.
Hold up, where did you get where you're gonna put A and B?
Right here. Right here.
Oh. Okay.
Linear.
So my rational functions can be written as the sum of partial fractions. And so by finding those coefficients, the A and the B, I'm now able to essentially take the antiderivative of 2 over x minus 1 and 3 over 2x plus 1. Okay. So we're going to take the antiderivative of each individual piece, that 2 over x minus 1, and of that 3 over 2x plus 1. So I want you guys to find the antiderivative of this. These dealt with the linear factors that you have to memorize, okay? So what did you get for the antiderivative of 2 over x minus 1 dx? 2 ln.
X minus 1. Whoa.
And then parentheses x minus 1.
Mm-hmm. Very good. And what about for the second piece?
Plus 3 halves. ln.
And then, no, of course, don't forget your plus c. So for the types of functions that are rational, that you cannot use substitution or any of the other methods that we are going to learn, you can create partial fractions and then take the antiderivative of those pieces individually. Sounds good.
Yep.
Okay.
I have to remember this.
That look. Yeah, the smile threw me off.
No, I'm saying, okay, we're gonna do another one. Okay, we're gonna do another one. But this is the last one of like the different I guess like rules or ways to find the integral. Okay, we still got to do trig. Okay, trig functions. If you know I haven't done any trig functions, they've all been like regular functions or exponentials. So yeah, but once we get through this last one, then we'll be able to look at trig and then keep on practicing.
Find the antiderivative of part sign.
Real quick, just to make sure, because I did forget about this, and I didn't have it in the video because it's not harped on in like other ones, and I ain't gonna lie, I gave y'all the SL video to watch. With the natural log, think back to natural logs or logs in general. Can you take the log of every number? No, so you always want to make sure that you can take the log of what types of numbers? Positive. So you need to make sure that when you do these problems, that you do include the absolute value of those essentially those arguments there.
So if we do not have it,
I don't necessarily know. I have to check a few mark schemes to see if they're going to penalize you by not having it.
so every time that we do the linear equation with the ln, we have to make sure that we have
The absolute values, yeah. And I also feel like, you know, when it comes to like if we have to do anything further beyond just finding the antiderivative, you're going to need to make sure that you are dealing with just the positive version of that number that you're taking the natural log of. All right, integration by parts. All right, integration by parts is a method that comes from the product rule of differentiation. It's another way that you can take the antiderivative of different types of functions, okay? So there's the formula, straightforward, like that. This rule allows you to find the antiderivative of u v prime dx, provided that u prime v dx can be found, okay? So we're just gonna jump into an example and apply integration by parts. Here we go. All right. If you look at this particular example, you find the antiderivative of, or the integral of x e to the negative x dx. If you think, okay, well maybe I can use substitution here, use substitution here. Well, that means you're going to be making u negative x, and then your tu is going to be negative 1, and then you got the x situation going on, and you
I don't like
might not be the best thing. This is definitely not a rational function, so we can't use the partial fractions, and all the other more basic rules that come with integration aren't going to apply here. So you're left with integration by parts. And so essentially what this breaks down to be is that these are your pieces, or your parts. This is your u, this is your v prime, and then you apply the formula accordingly, okay? So u is going to be equal to x, v prime is going to be equal to e to the negative x. In order for us to do integration by parts, we need their corresponding pieces. We need u prime and we need v. U prime is nothing but the derivative of u, which is what? So it becomes 1 dx. And then v is essentially the antiderivative of e to the negative x. What's the antiderivative of e to the negative x? Negative e to the negative x. That's another one of your linear factor ones. Remember, it's 1 over a, e to the ax plus b. A in this case is negative 1. There we go. So now we're able to apply the formula, which is, sorry y'all, it's been years since I've done integration by parts, so I am rusty. Sorry, let me rephrase. It's been a decade since I've done integration by parts. Like real talk. I think the last time I did integration by parts was, yeah, it's been a decade. It's been a decade. Yeah. All right. So plug everything in. U is x. V is negative e to the negative x minus the integral. U prime is 1. And then v is e to the negative x. And that 1 dx essentially takes care of the, well, it takes care of that dx there for you. Actually, no, it doesn't take care of it. You still need it. No apologies. The reason why we still need is we still have to take the antiderivative of e to the negative x. What's the antiderivative of e to the negative x?
It's e to the negative x. What? Yeah. Oh, wait, sorry, wait.
What's the antiderivative of e to the negative x?
Negative e to the negative x.
Negative e to the negative x. Okay, so we take care of this part where we're taking the antiderivative. Sorry, include the dx.
Isn't when you put the antiderivative, it just be, so it would be negative e to the negative x that you're taking the antiderivative of?
Yep, I missed the negative.
Okay.
Yeah.
Sorry. Sorry, y'all. I did miss the negative. So then it would be e to the negative x? Yes. Okay. So then that part's taken care of. Bring down the minus from on the outside of that yellow box. And this becomes negative x e to the negative x. And of course, we cannot forget our plus c.
They turn their cameras on.
So you have many weapons to use in finding integration of different types of functions. Okay?
I like the war imagery.
We're going to look at an IB example. I want you guys to give it a try. Or you're going to look at a few examples. All right, for you guys to practice with these other newer rules. And then we'll see where we are after we go through a few of them. There we go. This was gonna be your pod, but then I realized like I had to talk about it a little bit, so.
We can't do it.
I mean, you couldn't do it before, but now you can. It's not a pod, just add it to your notes. Okay, so by using the substitution u, so they give you what they want you to use for u, you have to find the integral of that expression. So if u is equal to 1 plus the square root of x, that means that du has got to be equal to what? What?
I have no clue.
I didn't hear you.
Wait.
1/2 x to the negative 1/2.
And that ends up being 1 over 2 x to the 1/2, right? Or the square root of x. Okay. So when you look at this, first off, you're kind of stuck in a position where you're like, okay, this isn't quite aiding or assisting me in a few things, right?
If you make it 2du equals root x.
You said 2du can equal,
Square root x.
It could.
You can do u minus 1 over
Well, it'd still be on the bottom.
it'll still be on the bottom. It'll be
Yeah.
1 over square root of x.
So du to the negative 2du to the negative 1. But I don't think that's the right direction.
Why is it not u minus 1 over u?
Why is it not u minus 1?
I mean, wait. Yeah. Because
Okay. Okay. So by taking this, you can say that u minus 1 is equal to the square root of x. Is that what you just said?
Yeah.
Okay. So the issue still lies in the fact that du is equal to 1 over 2 square root of x. So we still have that dilemma there. Say it again.
Could it be 1 over 2 times u?
1 over 2 minus 1? Yes, because I can replace that square root of x with the u minus 1. Okay, and I'm sorry, y'all, I forgot this dx. Maybe that might help. Just so you know, right now, we've replaced the denominator. We've replaced the numerator. The one thing we haven't replaced is that the dx.
So then we would just put the 1 over 2 times u minus 1.
There'd be 2u minus 1.
I would multiply both sides by that 2u minus 1 du, and then that would be able to replace my dx. So now I'll have all this times 2u minus 1 du. And considering that this is essentially 2u minus 1 over 1, that turns into 2 times u minus 1 squared over u du.
Yikes.
Questions? We're not done with this problem. We still have to actually do the antiderivative, but how we got to this point in the blue. That doesn't sound, doesn't roll up the tongue as easily as substitution. So from here, I can go ahead and pull out a 2, pull out that constant. What can I do to continue to take the antiderivative of this? Because I definitely can't do it the way it is now. What can I do? I can FOIL. Not integration by, I thought you were about to say integration by parts, no?
No.
We can FOIL. This be u squared minus 2u plus 1 all over u. That could break down some more, could it not?
It's over u.
Could you divide by u?
I can divide every term by u, so that would be u minus 2 plus 1 over u. You say you're confused?
No.
Okay. And so now I can actually take the antiderivative now, because it's in its most simplest form, right? What's the antiderivative of u?
Half squared.
1/2 u squared. What about antiderivative of -2?
-2x. Or u.
I'm going to use u for right now, then
Yeah,
we'll
no,
plug it in afterwards.
I'm just-
And what about the antiderivative of 1/u? Don't forget that absolute value bar. All of this needs to get multiplied by 2 because that constant was pulled out. So then this is going to be u squared, which would be, what was u?
1 plus x over x.
Thank you. So it'll be just u squared minus u plus 2 times the ln of u plus c.
Wait, where did the 2 go in front of the second term?
Oh, should have been a 4.
Okay.
Sorry.
That's a lot of things.
It is. Let me see. 1 plus 2 square root of x plus x minus 4 plus 4 square root of x plus 2 ln. Just simplifying at this point. No.
Boxing the answer as we had it.
Yeah. Maxime says for the correct expression for x, but not necessarily fully expanded or simplified. So yeah. But so this would be your fully simplified answer, the one down here at the bottom. But this one too would be acceptable.
Wait, how did you get to that stuff at the bottom?
I foiled the 1 plus the square root of x. That's how I got 1 plus 2 square root of x plus x. And then I distributed the 4 to be -4 plus 4 root x. Combine like terms.
But I could still have the first one.
Yeah.
If I want.
Yeah. Let's try this one. The function f is defined by that rational function that you see there. You're asked to find an expression for f to the -1 of x, which means the inverse, you guys, not the derivative. So to find the inverse, we go through a few steps. What's the first thing that we do?
Substitute f of -1 to y.
We substitute it in for y, and then we
You flip the x's and put it equal to f.
you put the x's and y, so this becomes x equals 3y minus 2 over 2y minus 1, and you have to go through the process of actually solving for y at this point. The reason why it's worth 4 marks is because, you know, in these types of problems, you have to do a little bit more algebraic manipulation, so then that way you can solve for y, such as distributing over the x, getting your y's on the same side, factoring out a y, and then dividing so that you solve for y. So the inverse of f to the inverse of f is going to be x minus 2 all over 2x minus 3. Did you guys get that?
Yeah. Yep.
Okay, so then out of these 7 points, you're good to go so far.
Right.
Okay. So now you have to find, see if you can close it in with the last 3. So given that f can be written in the form of that, find the values of constants a and constants b. So if that's the case, they're talking about the original, not the inverse. So if the original can be written like that, then remember, we're in order to be able to add these two together, you need to have a common denominator. So you would need to multiply a by 2x minus 1, and then b doesn't get multiplied by anything. All of that needs to equal your numerator of your rational function. So that means that 3 has to be equal to 2a, and -2 would be equal to -a plus b. Okay, since b is just a constant, then it only pairs up with the constant, not with the variable and the coefficient. So that means that a would equal 3/2. And if a equals 3/2, that means b would equal a -1/2.
I was
Question.
on the right track. I just doubted myself.
Okay.
It was okay.
So again, remember, when it comes to these partial fractions, you want, you know, those different pieces to match up. So all your constants go together.
Okay.
So now that you have that, essentially, you're going to be taking the integral of 3/2 plus a -1/2 all over 2x minus 1. But y'all know good and well we can't have a fraction within a fraction. So this actually is 3/2 minus what?
That's
-1
what we did.
over, or 4 times 2.
And then you'll take the integral of that, which is just what is this? 3/2x minus 1/4 ln absolute value of 4x minus 2 plus c.
When you were doing the antiderivative of what we found, that for that second part with the -1/2, did you flip the 1/2 or?
So on this part,
Yeah.
you can do, you know, keep, change, flip.
So we can choose to flip either one?
I'm flipping the denominator, which is the 2x minus 1. Because remember, b was your numerator.
Okay, I didn't.
Now you could avoid this part altogether by actually factoring out that constant and just having 1/2x minus 1, and then just doing it that way. So end up with the same answer.
Okay.
Yeah.
That's all I was confused about.
Just to summarize and to recap, okay? On top of all of your other, you know, more basic rules and your different ways of integrating, don't forget you also have, you know, U substitution and being able to manipulate different pieces of the substitution so that it works in your favor. You also have partial fractions for those rational functions that just don't quite work. You can create partial fractions and then be able to take the integrals of those, as well as integration by parts, which does allow you to do it as well.